Hi there! So today we will be continuing my artist-friendly math series by creating this procedural elevator grate and using some basic trigonometry to get that accordion motion of all those crossbars. So this is a sort of resurrection of a setup that I had made for my master's thesis, which was a virtual reality film called Castle of Annoying. We have some clips here. And I had originally created this gate more so for experimentation, but also to give me the ability to adjust the proportions of the elevator without having to hand model and recreate animation. So let's look at what this setup can do here. Okay, so here we have the elevator gate, and looking back at this setup, it is a bit needlessly complex, so I'm going to recreate it a little bit more simply. And that's something I've noticed is a good sign of progression in Houdini if you look back at an old setup and you think, wow, what was I thinking? But anyway, the same basic principles here apply. So I have the gate and I can animate this, and all these bars here are rotating correctly around these anchor points here. So you could kind of do a traditional rig or look at constraints, but we could also do something like this just with math. And that's a very simple sort of flexible setup where now I can do things like adjust the number of bars here, maybe adjust the whole length of this gate, and then this whole animation is still going to play correctly. So it's a very flexible setup here. And you could kind of remodel and apply any sort of geometry or look to this. This could be applied to other sort of setups where you have this sort of mechanical pivoting action. And yeah, it's pretty fun to experiment with. So let's sort of break this down in a very simple way here. So I've recreated this setup just with a few less nodes. It is all based around a line. So this line is determining the number of vertical bars that are in the elevator gate, as well as the movement of everything. So I'm taking a line and then I'm just copying some vertical boxes to those points. That's pretty self-explanatory, and you could replace this box geometry with any sort of ornate like metal rod or what have you. I'm also copying more geometry for these cross slats. So if I take a look here, these cross slats are just also simple boxes, and I'm doing some mirroring operations. I'll just disable this so we don't worry about it for now. And then I'm just copying them more times with a copy and transform to get that height. But let's look at like just one crossbar and see how this is working. So if I go back to my line here and I adjust the length, this angle is dynamically changing, and that cross beam is sort of pivoting at that bottom pivot right here, maintaining its length. You see if I go too far, it'll disconnect, but then we can put it back and it's all working. I can dynamically adjust the number of points and everything updates just fine. So the root principle of this is based around trigonometry. If you remember that fun catchphrase, SOHCAHTOA, this is something I don't readily have within my knowledge bank. So when making a setup like this, I definitely had to look back and remember exactly how to calculate this stuff. But if we look at this shape here, we have a triangle being formed. So I'm going to just cut for a second and draw a picture and help us better understand how this is working. Okay, so let me start off by saying I am definitely not a mathematician, so my apologies if I misrepresent any of this information. I am simply trying to use some math concepts to make interesting 3D visuals and aid in that development. So we are going to use this trigonometry rule to figure out how much to rotate these crossbars. So if I just jump back to Houdini for a second, we're copying these crossbars vertically, and we're looking to see how many degrees do I need to rotate this in order to have it match up with that vertical beam there. So I'm missing this angle. This is a dynamic angle that'll change, and I'm looking to calculate that angle. So you can see here, I have sort of traced in red this triangle that's forming due to these crossbars, and I could also just draw it over on this side too. We have these two right triangles, right? We're trying to find out one of these angles in order to determine how much to rotate this beam so it lines up over here. So to do that, we can use this one right here. This angle, since we have a right triangle, is equal to the cosine of the adjacent edge, the length of the adjacent edge, divided by the length of the hypotenuse. So that is this formula right here. Cosine of that angle equals adjacent over hypotenuse. And then we can find this angle, or theta would be the math term here. That angle equals the inverse of cosine of the adjacent edge over the hypotenuse, the length. So we actually have all this information here because we are creating it. So we know, so this is the hypotenuse, right? We know the length of this because we're making that box. We know the length of this bottom edge. This is the adjacent edge because that is the length of the line divided by the number of segments of the line. And that's all we need. So if we divide these two lengths and just use an inverse cosine function on it, we will get that angle, and we can use that to dynamically drive our elevator animation. So now let's jump back into Houdini and take a look at how we can implement that. I just keep thinking of that Key and Peele sketch. I wish I was high on pot news. Anyway, let's look at how we can implement this with a little bit of code now back in Houdini. So in order to do this, I just made an attribute wrangle. So these are the nodes that we can use to write Vex Code, which is Houdini's scripting language. And we can see right here, we just have a few lines of code here that is recreating that equation that we just saw. So what I'm doing here, I'll copy and paste this into the description of the video as well. I'm making a couple of variables. So I'm making a variable for the length of the hypotenuse, and I'm making a variable for the length, I just called it base, for the base of the triangle. And this syntax right here, CHF, that means channel float. So that'll create these sliders up here. So I have a place to input both the hypotenuse and the base length. And then I'm just writing that, that formula we have. So I'm creating a variable for angle, so that F is for float, and then the @ sign is for an attribute. I'm creating a float attribute for angle, which is equal to the inverse cosine. That is what that A cosine function means. And I am passing into it the length of the base divided by the length of the hypotenuse. So that is literally this equation right there. And then this very last line of code here is just to flip the angle. So if I remove this 90 degrees, you can see it's just facing the wrong way. I just needed to flip it with that minus 90 here. And so I'm just applying that result of the function back to the angle attribute, and that's how that is calculated. Now, just to point out here how these variables are being parsed. So the hypotenuse, what I'm doing is using a relative reference of the size of the box. So we can see here when I click on the text, it reveals the reference that this channel is pointing towards. So it's looking at box 8, and it's looking at the size of it. So if I kind of go over here and find out where my box is, box 8. This is what is forming the crossbar here. So I can sort of adjust this, and you can see that angle is updating because the formula is referencing that length. So that is the hypotenuse, the length of this box. If you had your own custom geometry, you could just do something like measure it, measure the height of it, and use that instead. But this is pretty simple since we're just using a box. I can reference the length of the box directly. And then for the base, I'm taking the length of my line here, and I'm just dividing it by the number of segments. So the expression here is looking at that distance of the line and then dividing it by the number of points minus 1. So you can think if there's 3 points in the line, for example, let me show my point value, that would be 2 segments. So the number of segments is just the number of points in your line minus 1. So you divide the length by the number of segments to get the length of each segment here, and that is the length of the base. Hopefully that's all making sense. And once we have that implemented, I can just copy and paste. Well, I can't really copy and paste, but I can apply this angle attribute to a transform node. So if I look at this transform node, this is what is actually rotating this box here. I'm going to go ahead and look at the end of the setup. So this transform node occurs right after the box geometry, and it is referencing this angle attribute here to get the correct rotation. So this attribute wrangle right here is set to detail, which means it just happens once. It just executes the code once, and it creates the attribute on what's called the detail section of the geometry. So if I go to my attribute spreadsheet, I have those angles, base, and hypotenuse attributes. And I can reference those on any other node just using this detail expression. So I'm just taking the detail, and I'm pointing towards the node that calculates it, which I just named calculator. And then the next word here is angle, so that's what attribute I'm referencing. And the last input for this expression is 0 because it's just a single float. If you had like a vector or an array, that last slot in this expression is to designate which one it is referencing. So for us, it's just going to be 0 because there's only one value there. And so now this number will just automatically update based on this math right here. And so what that does for us is, let me kind of reorient our screen here. What that does for us is allows us to adjust the length, adjust the number of points, animate any of these attributes, and have everything dynamically adjust. So that's really cool, really powerful, very quick to process. And to get the more details that I had in the renders, you can just add some nodes, like to get the cross beams, I'm just mirroring that initial setup. And then I use a transform node just to shift it over to the left. This transform node is referencing that same calculator and using the length of the base to shift it over the right amount. I can use a copy and transform node just to make as many vertical copies as I want. I could really go nuts with this. And then I could change the length of my crossbars, and now I have a super tall gate. And then if I animate the length of the line, everything is still working here. Very robust setup. To get some more like sort of abstract effects, I was playing around with making an initial gate, and then you can always apply certain deformations after the fact. So in this case, I'm adding a transform node just to change the orientation of the gate. And then I'm using a path deform to rotate it, or sorry, not rotate it, but actually deform it around a circle. So in that first render or the render at the start where it was around a spiral. That's how I was doing that. So I could change the size of the circle and start getting the gate to wrap around. So now I have a sort of enclosure, and I can still go back, animate the length of this gate, and everything is still working. All right, so that's it for this one. I hope you enjoyed it. I hope it's helpful. If you make anything with it or have any more questions, let me know. Have a great day.